G'day, the central concept to this whole question, apart from the working scientifically skills of graphing, is impulse. Now, impulse is the change in momentum. That's it. It's kind of tempting to go, is it the rate of change of momentum? Change in momentum divided by time, like acceleration is the rate of change of velocity. No, impulse is simply the change in momentum. All right, so let's have a look at this question. We are going to generate a change in momentum of one of these carts by applying a force over a period of time, and we've got our force sensor there. And of course, if you know me well enough, you'll know that I would have set this experiment up, and here it is. So to create a repeatable initial velocity for the cart coming in, I have put a slight angle, you can see on that table on the left, and so it goes down a very slight ramp, a fixed distance up that ramp, and so let's hope it's going at a consistent speed when it makes the collision. And the first collision we're going to do as it comes down this ramp is to use that nice kind of soft spring that is on those physics carts that we have. It makes collision. You can see the black device there. That is the actual force sensor that we're using, just one of those vernier force sensors with a little hook unscrewed, and so we've just got the basic metal plate where it lands. Then I had to think about, how do I change the stiffness of a spring? What is the stiffness of a spring? Well, it's why some things are soft and some things are hard, right? What makes something soft is that as you deform it, the force increases only quite gradually with the amount of deformation, and so the time of the collision is longer. You imagine, you're lying down and you just let your head go down on the pillow. The reason it doesn't crack your skull open is because the duration of that collision is long, because there's a small force to start with, and that slowly increases in a nice sort of gentle way, and then your head comes to a rest on the pillow. That doesn't hurt. If I was to replace this with a sack of concrete and you slammed your head into it, that would hurt, because it creates a very large force with a very small deformation. So if you think about something that's quite rigid and quite firm, as you push on it, as it deforms just fractions of a millimeter, the force increases really quickly. That massively reduces the time of the collision. We'll come back to that in a moment. So I thought, okay, what we'll do is we'll just use the elasticness of the plastic at the end of the trolley, and we'll just have the plastic end smash into the force gauge. And so let's have a look. And there you have it. Now you can see the overall before and after is the same as it was before. This cart comes in with a velocity, it stops, this cart leaves with that velocity. But what changes is that duration of that interaction. And here's the two screenshots I got from the data logger. Pretty hard to see what's going on because they've auto-scaled the graph. So I've exported the data and made a graph of it. Here it is here. Notice this little artifact here on the first one with the spring out, right? There's this little kind of peak. That happened a number of times when I did it, and it was quite consistent in the results. And I think what that was that aluminium tube with the spring inside. And I think there's a bit of sloppiness, and so the aluminium tube, the end of it, makes contact with the force sensor before the spring makes contact with that aluminium tube. But nevertheless, we've got this lovely long time of an interaction and a very kind of low peak force. The magnitude of the force doesn't get very great. In the second one, the blue one, you can see that it's a shorter interaction time, and therefore the peak force has to be greater. Why? Because impulse is the force times the time, and if I'm plotting force on the y-axis and time on the x-axis, force times time is going to be the area under that curve. And so the area under the orange curve is the same as the area under the blue curve, and therefore the peak force has to be greater. Now, that underpins a lot of the collision technologies you'll find in vehicles, because from the point of view of the person, it doesn't matter how long the force lasts, as long as it's less than what's going to break your bones or rupture your spleen or cause brain damage. You want to, paradoxically, you want to have a collision. If you're in a car, you want to have that crash last as long as possible from your point of view. The more we can spread it out over time, the lower the magnitude of the peak force. That's one of the two principles that all of our collision technologies work on. So how's this principle applied? Well, the basic one is the idea of crumple zone. So if this is the front of the car and this is where the passenger or the driver is, the front of the car comes to a stop, you continue moving, Newton's first law. The longer we can keep you moving, the longer we've got to apply that force to bring you to a stop. So instead of having a rigid, strong car, they're actually not safe. You want a car that allows you and the passenger cell to continue to move for as long as possible. Even seatbelt pre-tensioners, so these are explosive devices that go off that take the slack out of your seatbelt the instant the car has detected that it's in a crash. So what that means, instead of wasting time while you continue moving forwards into the seatbelt before the seatbelt starts to apply a force on you, if we can bring that seatbelt back and have it applying a force on you the instant the collision has happened, then we've got a longer period of time for that force to be applied. Now, the second principle is to spread the force out over area. So the first one is to spread the force out over as long a time as possible. The second principle is the biggest area, because 2 forces at 1 Newton is going to less likely to cause damage than 1 force point at 2 Newtons. And so the more we can spread that force, we can reduce the pressure at any one point, or the magnitude of the force at any one point, the less likely there's going to be an injury. And that's what those lap sash seatbelts, which are now mandatory even in the center back seat, because that sash applies that force over a much larger part of your body. It also applies it for your upper body so that your head doesn't keep moving, and then your head has a collision with something hard in the car, which is going to be a very short duration collision. An airbag, instead of your head continuing forward and hitting the windscreen and coming to a stop in a very short period of time, and therefore a large peak force, the airbag increases the time of that duration. It also increases the surface area. So instead of that force being concentrated here where you hit the windscreen, it's spread out over your entire face. So car manufacturers have those 2 principles, spread the force over time, spread the force over area, to work on. There is one other thing you can do, and that is try and make the collision as inelastic or plastic as possible. So if it's an elastic collision, then it comes in with a certain momentum and it bounces back, and so now you've got twice the change in momentum. If you can just bring it to a rest, you've halved the change in momentum. And that happens in more plastic or inelastic collisions. So these crumple zones are designed to crumple and not spring back. So when they talk about energy absorbing, it is absorbing the kinetic energy by being inelastic rather than returning the kinetic energy by the object bouncing back. So physics is amazing, of course, and it's everywhere. It explains why when you drop your favorite mug on the tiles, it's more likely to shatter than if you drop it on a timber floor or a lino floor, because those other floorings have a longer duration of that collision, and therefore the peak force is going to be less. When you put your head on the pillow at night tonight, remember why the pillow is soft. Enjoy.